It's time for our first problem, or I like to think of them more as puzzles. We have to find the missing pieces and put them together and see what we can figure out. It's a puzzle. All right, so in this case, we've got a person sitting on top of cart B, and their feet are up on cart A. Sorry, that's as good as I can do with my drawing ability. So we've got our initial condition here. Nothing's moving. Cart A is stationary. Cart B, with the person sitting on it, is stationary. Nothing's moving. And then the person kicks their feet out, straightens out their feet, and their legs exert a constant force of 40 newtons on cart A as they extend their legs. And the distance that cart A moves while the person is extending their legs is delta x, or 0.7 meters. So that's the given information in this problem. Everything starts at rest. The mass of cart A is 14 kilograms. The mass of cart B, including the person, is 70 kilograms. The legs exert a nice constant force of 40 newtons. They're well calibrated. They always exert a 40 Newton force as they extend. And the distance that cart A moves is 0.7 meters. We're going to examine this problem through all four of our lenses. We are going to look at forces, energy, momentum, and kinematics. So let's start with forces. Why don't you stop the video and think about what you can tell me using forces and our force equation F equals ma. Let's take a look at our equation F equals ma and think about what each of those variables means. F is the net force acting on cart A. M is the mass of cart A. And A is the acceleration of cart A. Make sure you understand what each variable in the equation stands for. In order to use this equation, because it's a vector equation, we need to define our coordinate system in our positive directions. I'm going to call the right my positive direction. So I can rearrange this equation. I get the acceleration of cart A is going to be the force on A divided by the mass of cart A. The force on cart A is 40 newtons in the negative direction. The mass is 14 kilograms. That gives me 2.86 in the negative direction. Units for newtons are kilogram meters per second squared and kilograms for mass. So I get 2.86 meters per second squared in the negative direction. Using forces, we found the acceleration of cart A, and it was 2.86 meters per second squared. Remember, the units for acceleration are meters per second squared. The cart's velocity will change by 2.86 meters per second every second in the negative direction. Now see what you can figure out using energy. Let's start out using work. We know that work is force times some distance, dx. So our work done on the box by our force from our legs is going to be 40 newtons times 0.7 meters. That's the distance that the force acted on the box. 28 Newton meters and we know that a Newton meter is a joule as far as energy is concerned. Joules are units for work and energy. So we found the work done on cart A by our legs. Now we know something else about energy and work. They're related, right? Work tells us the change in energy, in particular, the change in kinetic energy. And we know that change in kinetic energy is always final minus initial. K final minus K initial. So the work done is going to be the final kinetic energy, 1/2 ma times V final for cart A squared minus 1/2 ma V initial for cart A squared. And V initial, we know, was 0. So the cart had no kinetic energy at the beginning of the problem. It only had kinetic energy at the end of the problem. So I'm just going to multiply through by 2. I've got 2 times the work done divided by the mass of cart A equals V final A squared. I can take the square root of both sides. So V final for cart A is equal to the square root of 2 times the work over the mass of cart A. So I know those things. I can plug them in. I have 2 times 28 Newton meters all over 14 kilograms. And that's going to give me 14 goes into 28 twice. That's going to give me 4. And a Newton is a kilogram meter per second squared, and there's a meter there. So this is going to give me meters squared per second squared. Wait a minute, that's not velocity. Oh, I forgot to take my square root. So I forgot my square root. There we go. That's better. 2 meters per second. So sometimes carrying units along helps you catch a silly error. All right, so we know our final velocity of cart A now. And I think that's most of what we're going to get from energy. So energy gave us the work done on cart A by our legs, 28 joules. And that's a scalar. Energy and work are scalars. Now, here's the tricky part. Because we used a scalar, we used work done to calculate the final velocity of cart A, it didn't give us the direction because we took a square root. And what we should have done when we took that square root, we should have said b squared equals something. V is equal to plus or minus the square root of that thing. And really, in this case, we should have had the negative root. But we found the magnitude of the velocity with this equation. 2 meters per second is the magnitude. And of course, if we look at the problem, we would know it has to be going to the left. So that part we would have to add in. Now we can use momentum. So see what you can figure out using momentum, and then come back and we'll do it together. So because all the forces are internal to our system, if we define our system as the 2 carts and the person, the legs pushing on cart A and cart A pushing back on the legs, those are all internal forces if we define our system as being the whole thing, cart A, cart B, and the person. Nothing reaches in, and therefore momentum is conserved. So we know that we started out with no momentum. So the initial momentum of cart A plus the initial momentum of cart B, and those are both 0 because nothing was moving initially, has to equal our final momentum And the momentum of cart A is its mass multiplied by its velocity. And the momentum of B is the mass of B times V final B. And this is a vector equation, so I can keep the signs straight and it'll give me the correct sign for the velocity. So I know that my mass of cart A is 14 kilograms. The velocity is negative 2 meters per second because it's 2 meters per second to the left. The mass of B is 70 kilograms. And its velocity, well, we are solving for that, aren't we? And what we get here is that V final B is 28 kilogram meters per second over 70 kilograms, or 0.4 meters per second. And because it's positive, we know it's to the right. Can you use momentum to find the time interval that the legs and the cart were interacting? In other words, how long did it take in time, in seconds, for the cart to move from where it started to go that 0.7 meters? Well, we can use impulse to find the time because we know the change in momentum. So rearranging this equation gives me delta t is my change in momentum over my force. And we know change in momentum is P final minus P initial. Using cart A, because we know that the time interval is the same. When cart A is pushing on the legs and the legs are pushing on cart A, they interact for the same amount of time. Cart A can't push on the legs longer than the legs push on cart A, right? The time interval is the same. So as long as we use one item, as long as we stick with cart A for everything, we're fine. Or we could have stuck with the legs in cart B for everything. That would have given us the same answer. But let's just stick with cart A. The final momentum we found earlier, it's 28 kilogram meters per second in the negative direction. The initial momentum was 0, and the force from the legs on cart A is 40 newtons in the negative direction, to the left. It's pushing the cart to the left. And a newton, we know, is a kilogram meter per second squared. And so this whole thing gives us seconds. 0.7 seconds. Using momentum, we found the final velocity of cart B, and we found the time it took for cart A to move those 0.7 meters to the left. Now let's take a look using kinematics. See if you can draw the velocity versus time graph for cart A. So let's see if we can fill in the velocity time graph for cart A. Cart A starts out at 0 meters per second speed, and it ends up at 0.7 seconds moving at 2 meters per second in the negative direction, negative 2 meters per second. And what does the curve look like between these 2 points? It's going to be a straight line. And the reason is that the slope of this line is our acceleration. And our acceleration is constant because the force from the legs pushing on the cart was constant. It didn't change. So our acceleration is constant. So anywhere we look, if we look at t equals 0.1 seconds, t equals 0.2 seconds, t equals 0.3 seconds, any of those places, the slope of the line has to be the same. And that means it's a straight line. And what's the average speed? Well, because it's a straight line, we can find the average speed just using the endpoints, and we get the average speed is -1 meters per second. So we can take V average and multiply it by the time to get the distance that the cart moved, the displacement of the cart. And the displacement of the cart is going to be (0.7 meters in the negative direction. The cart moved by 0.7 meters in the negative direction. We knew that already, but that's just a good way to double check. Check. We got it right. We got the same answer that was given to us. And there's another way to get this distance. The other way to get this distance is from this graph. Because the area under the curve of the velocity versus time graph tells us the displacement. So if we draw this, we look at the area under this curve, we will get our displacement. And the area under the curve is, this is just a triangle, 1/2 base times height. So it's 1/2 0.7 seconds, -2 meters per second. So I'm getting 0.7, -0.7 meters. The displacement is 0.7 meters in the negative direction. So it's nice when things come around and you can check your answer by calculating it a couple of different ways. And this is just an example of what we're going to do for every problem we see this quarter. We're going to take a look at it using all of our lenses. What's going on with forces? What can we figure out from the problem using forces? What can we use energy for? Can we get any useful information from energy? How about momentum? Let's take a look using momentum and see what that tells us. How about kinematics? What information can we get from that, or can we double check some of our other answers? And that's going to be how we do every problem.